All right, so we look at an example of terminal and bridging carbonyls, and how can we tell the difference between these two things in an inorganic complex using IR spectroscopy. So there was this example structures it that there was some elemental analysis done and some general chemistry knowledge done and of course the knowledge of the synthesis that happened beforehand to get us to a point where the inorganic complex looks something like one of these two options. Now, the first thing that we probably need to do is try and identify any differences between them. So let's start with these big groups. So we can see these big groups are present in both molecules, right? You might have immediately seen the differences between the two molecules, but that's also okay. The next thing is this one has 1, 2, 3, 4 carbonyl or CO groups bonded to it, and this one only has 2 in a terminal fashion. So remember, terminal fashion means that there is, so it's C triple bond O, and then it forms one bond to that. Maybe that's not the greatest way to indicate it. It forms one bond to the metal center. And the next thing that we also need to really investigate or look at is that both of them are dimeric structures. It means there's a bond between the metals, or at least one bond between the metal atoms. Now, so in other words, this one on the right, we've already allocated all the bonds in it. On the left, there's still 2 bonds left. So those bonds are what distinguishes these two structures. So it means we have a bridging carbonyl ligand in these structures. So that's essentially what we're trying, or what we're going to look at in its IR spectra, to see if there are any differences. Now, looking at the IR spectrum, the important information that we're given is that this spectrum is indeed run in nu-joule mole. So it means that's something we need to, so the mulling agent is nu-joule mole, and that's something we also need to consider. So for example, peaks from nu-joule mole is not applicable, not important in the spectrum. And the next thing is then we need to try and figure out which of these peaks would typically give rise to a terminal versus a bridging carbonyl ligand. So I think we start with the nu-joule mole. And if you look at any nu-joule mole spectrum, you'll see that it gives rise to this peak and these 2 peaks. So those are the 2 that we need to ignore strongly. The next thing is we know where we expect terminal versus bridging carbonyl stretches. So we look at 2 ranges. We know we have a range between 2,200 to 1,900 per centimeter, and that is per centimeter. That means terminal CO. Okay, so we see a bond stretch in that region. We know it's terminal. Both of these complexes contain terminal carbonyls, so that's not really going to give us any indication, but it still will confirm that there is indeed terminal CO bond stretches in these complexes. We also know, so then the next thing that we need to look at, the region between 1,900 and 1,600 per centimeter. Per centimeter is equal to bridging COs, carbonyls. So let's then now finally look at the spectrum. So the region that we're actually interested in, or going to look at, is the region between 2,000, so 2,000 whatever, and 2,200 and 1,600. So in other words, this is the region that will help us really distinguish between those two kinds of stretches. And we see here we have a stretch at round about 1980 per centimeter, and we also see a stretch at 1770 per centimeter, which is the one on the right and the other one's on the left. So what does that indicate? So this first stretch, the 980, like approximately, per centimeter stretch, implies to us that we have terminal CO stretches, and that we then can confirm that both of these structures have terminal carbonyls. But the other stretch, the one that lies between 1770, of course lies in this range. So this one corresponds to something in that range, very strongly in that range, very distinguishable between these two peak vibrations. So we can then allocate this to, we must have a bridging CO stretch. And maybe let's take that off. That completely ruins things. So bridging. So in other words, the complex that we're actually interested in is then structure 1, because we saw bridging stretches. So it's not a fully out written argument here, but it's basically the logic that you need to use to solve the problem. So you can go write it out in paragraph form and get a nice way to describe why this is what you observe and why do you state that you choose structure 1. So of course structure 1 is it, and it's because it has the bridging stretches which we see there at 1770 wave number. All right, so that's what typically you would do, and I mean this is the kind of thing that you do for any kind of IR spectra where you're considering 2 kinds of structures or maybe 3, and then you'll assign these peaks. These numbers, of course, are listed in the tables that I provide you, so you'll be able to access those in any exam or test. All right, so I think that is it. Thank you for watching.